I see this. Is it started? Okay. This is going to be fun today, I think. All right. Let's begin with a word of prayer. Heavenly Father, we thank you for the weekend just completed. Again, Lord, we thank you for your mercy each and every day. We thank you that you've created the universe in such a way that we can understand it. And we thank you for the privilege we have to be created in your image, that we were fearfully and wonderfully made so that we can understand the universe around us, Lord. We thank you for your many blessings. Just pray that you'd add understanding to the students this day and help them ask good questions as occur. In your name I pray, Lord Jesus. Amen. All right, so any questions about branch cuts or anything? I asked you guys to read a few pages about it. Any questions? Let me just say a word or two about the square root problem. So, because I kind of muddled it last class, so just a clarification, I hope. Nothing too earth-shattering. Basically, if we're going to solve z squared equals to w, what you can do, essentially, is just say, I'm just going to go down to base principles. That's, modulus of z e to the I theta, quantity squared, equals to the modulus of w e to the I, let's call it beta, for the sake of discussion. And so what that is, of course, is the modulus of z squared e to the 2I theta is equal to the modulus of w e to the I beta, all right? But in order for this equality to hold, what we have here is a vector expression, right? We have a magnitude, and we have a direction vector and a direction vector. Those have to match up, right? So in particular, this gives us the modulus of z squared is equal to the modulus of w, which of course gives us the solution what? Modulus of z is equal to the square root of the modulus of w. Now here I just mean garden variety, honest to goodness, pre-calculus. Wherever you first learn square root, it's that square root. This is the square root of a real number, right? And then on the flip side, of course, if we have e to the 2I theta is equal to e to the I beta, what's that tell us? How can those be equal? That means what? 2 theta is equal to beta is part of the truth, but it's certainly not all of the truth. Plus right? 2 pi k. Yeah, plus 2 pi k for k an integer. Those are the possible solutions, right? So if I solve for theta, this gives me theta is equal to beta divided by 2 plus pi k. For k equals to what? 0, plus or minus 1, so forth and so on, right? But here's the thing. When you look at that, so we've got our solutions then are the form z is equal to the square root of the modulus of w, right? E to the I beta over 2 plus pi k, and I can simplify that a little bit, right? That's the square root of the modulus of w e to the I beta over 2 e to the I pi k. So what is e to the I pi k, though? That's cosine pi k plus I sine pi k, right? By Euler's formula. And sine of any multiple of pi, any integer multiple of pi is 0, right? And there's a nice formula for the other thing too. This is just what? K is equal to 0, it's 1. K is equal to 2, cosine 2 pi, 1. But cosine of pi and cosine of 3 pi and cosine of 5 pi, they're all minus 1, right? So a nice formula for this is just minus 1 to the k, right? So what do we get? Z is basically equal to modulus, square root of the modulus of w, e to the I arg of w divided by 2 or minus that, right? So I can just say z is equal to plus or minus. And by definition, and so here I'm suggesting to you that I could, going back here, I'm saying, okay, so, set beta equal to the arg of w. It's just making a choice, right? Whatever choice I make, the opposite solution is just minus that one. So either I choose beta so that I get the principal square root, or I choose beta so that I get minus the principal square root in this solution. But anyway, however you do it, you end up with just plus or minus a set of solutions where you have plus one and minus the other one. Okay, so more to the point. Z to the 1/2 then, W to the 1/2 is equal to the square root of W, comma, minus the square root of W. Now, I say square root, but what should I say to be more honest? What am I really saying? I mean, there's something hidden here, right? This is by definition the principal square root. So that's the square root of W is actually the square root of the modulus of W, and that's an honest to goodness plain old garden variety square root, and then exponential of I arg of W divided by 2. I would also point out that the way we find the set of square roots of W is to find the principal root and then multiply by the root of unity. So what is the root of unity here? I mean, this is another way you could look at this is the square root of W, comma, omega square root of W. Omega is unfortunate. Let me make my W's extra pointy. So here, this omega, remember, was e to the 2 pi I divided by 2 in this case. So that's e to the pi I, which is minus 1. More generally, if we look at the nth roots of W, right? If you want to look at the nth roots of W, what you do is you've got the principal nth root of W, and then maybe W is a bad choice. Let me do Z here. I'm going to do Z because that way we don't have the W omega degeneracy. So Z, the nth roots of Z. I don't want to do W. I'm sorry, guys. W. I'm just going to use a different letter for the nth root. I'm going to do this thing. Zeta all the way out to zeta to the n minus 1 power times the nth root of W. Where here, zeta is equal to e to the 2 pi I over n. So the point is, and the principal nth root is what? You take the nth root, the ordinary garden variety nth root of the modulus, right, which is a positive, it's a non-negative real number. We can take the nth root of that. And then we take the exponential of I arg of W divided by n. And then multiplying by zeta squared, zeta cubed, all the way up to zeta to the n minus 1, that generates the rest of the roots. But the square root is particularly nice because you don't really have to get into the details of zeta squared, all the way up zeta to the n minus 1, because zeta is just minus 1, right? So we can capture all of the square roots, even in the complex case, by just putting plus minus. But you got to be careful. The square root is not the simplest thing, right? It's the principal square root, and it's this. It's not maybe what you're thinking if you're being too naive. Now, in terms of the mapping, branch cut idea, right? Getting back to that again. First of all, let's think about a local inverse, right? Basically, here's I'm going to look at just a pi sector. I'll look at out just to keep things simple. I'm going to look at a little sector of the unit circle. And so from, basically the top is what, pi over n, the bottom is minus pi over n. And if you look at the z to the n function, what does that do? It blows it up into the left-seeking Pac-Man, right? Jump, 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 jump. So with respect to that domain, that little pie-shaped wedge, you have, assuming I don't include the edges, right? For a second here. I cover the slit complex plane, right? I cover C minus. So this is, usually we think about this as W is equal to Z to the N. So I take this wedge, and then it blows up to the whole circle. So the inverse map here is the principal square root, right? I said square, I mean principal nth root. Now, if instead I looked at another wedge, right? Maybe this one up here, right? What would that do? Again, under the z to the n mapping.
It would make a Pac-Man with his mouth hanging down and to the left.
Right, yeah, something like that. Yeah.
Pac-Man is now a mathematical term.
For the purposes of this discussion, yes. Something like that. And then you could study how those compare, right? I mean, for the square root function, I mean, this, the set of all square roots, the one branch and the other, at least the principal branch and the other one obtained by multiplication by -1, they're just related by -1, but more generally they relate by some phase factor, as discussed in my notes. But I'll let you read that. We'll come back to it when we need it later in more detail, okay? But this one actually I don't want to pursue further. I want to talk about the exponential more, because there I can actually draw the picture better. Gamelin tries to describe something called the Riemann surface on the basis of the square root function. I mean, he doesn't try, he does describe it. It's good. I want to try to describe it for the exponential function again. Oh, which problem was that? Was it problem, I think problem 4, you guys. There's an if and only if that if the modulus of z plus w is equal to the modulus of z plus the modulus of w, that's true if and only if z is equal to c times w, like it's a scalar multiple of the other. This is clearly false if one of them is 0. All right? I mean, it could be that's not true if one of them is 0. You can't write a non-zero one as a scalar multiple of the 0, right? So you should assume in that problem that it's given that z and w are both non-zero. That will make the problem more interesting, okay? The other thing I would add is that probably the easiest way to do the forward direction is geometrically. If you use the law of cosines, you can prove it without too much difficulty. I have an algebraic proof. I'll post. What's that? Anyway, I'm inventing new words today. So let's go back to the exponential function again. And I want to talk to you a little bit more about the idea of the branch cut and a corresponding idea, something called the Riemann surface. So we learned if we have e to the z equal to, what was it, e to the x times e to the iy. So in detail, that's e to the x cosine y plus I sine y, right? So if I look at this function, it's what can we say? F of what? F of z is equal to f of z plus what? Plus 2 pi I k for any k in the integers, right? And so if you look at a horizontal strip, right? Let's see here. Like this one, I think I did last time. So here you've got y is equal to pi, y is equal to minus pi. What happened with this, if we study this mapping, what would y equal e to the pi be? If you put, right? I mean, saying if you study the top curve, right? What is that? That's y equals, that's z equals to what? Z equals to I pi, right? What is f of I pi? If I plug in I pi, I get what?
E to the x times 1.
Oh, sorry. This is I'm not being careful enough. This is x plus I pi generically. The one I wrote was this point right here to start with. So as x varies, what happens? You get e to the x goes what? Larger and larger and larger. As you go to minus infinity, e to the x goes to 0. As you go to plus infinity, e to the x goes to infinity. E to the I pi, well, that's always minus 1. So this red line gets mapped onto this. I mean, except if it's excluded, it gets mapped onto this, right? And how about the minus pi? The same thing, right? So what about the rest? If you take a vertical line, say like this, that would be x equals to what? X equals to x naught, something like that. So what do you have? Feed that into here, you get e to the x naught, and then the y is free to vary between minus pi and pi. That gives you a circle of radius e to the x naught. So this maps to a circle of radius e to the x naught. And if you throw out the pi and minus pi, it gives you that, except for the, right? So here. And so if you look at it, right, as x goes to minus infinity, you get circles smaller and smaller and smaller and smaller and smaller and smaller and smaller, right? And as x goes to infinity, the circles get bigger and bigger and bigger, and so they just fill out the whole W plane, right? But there's this one pesky place right here, right? So okay, so the inverse map is what? As long as I throw out one or both of these horizontal lines at plus or minus pi, we don't ever hit any point twice, right? As it turns out. So the inverse map is log, capital log of W. This is the principal logarithm. So is the exponential, is the exponential 1-to-1? Well, no, right? How could you make it 1-to-1? Right, the one thing, yeah, exactly. The one thing, just what we did here, right? You could cut the domain down, right? Cut the domain down to just this strip between 2 pi of height 2 pi, and of course I could shift this up and down, right? I could just as well do any horizontal strip of that 2 pi height 2 pi would work. And we derived last time that the formula for this was what? Natural log of the absolute value of w plus I arg of w, right? Now, the origin's hopeless, right? That's out of there. So this is really for w in the slit complex plane in our current setup, yeah? But of course, if you solve the equation e to the z equals to w, if you solve that for z, what do you get? Yeah. Yeah, I mean, so just not to reinvent, I mean, we did it all last time, but of course one solution, I mean, let me just not reinvent the wheel here, but what you get is that z is, well, I could say z is an element of log of w. Where log of w is a set of values, right? It's actually equal to the capital log of w plus 2 pi I z. Yes?
So is the capital log kind of like the capital R?
Mm-hmm.
And then like little...
Right, capital log is like capital arg. It's a specific function. It's a particular choice of all of the infinity of solutions there are for e to the z equal to w. There are infinitely many solutions to that.
Little log contains all of it?
Little log has all of the solutions. And they're related through a pretty simple way. They're just related by multiples of 2 pi I, integer multiples of 2 pi I. So it's not too bad, really. And that ultimately, of course, goes back to this periodicity of the exponential, right? Because what this is saying is that, like, this point, and 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 this, and you get the idea. They're all, let's see, if that's, what is this? Suppose this is, 4, right? All of these are mapping to e to the 4, which is kind of a big number, but it's like here, right? All of these different things under the exponential, they're all mapping to this one point, right?
That's why it's not 1-to-1.
It's not just not 1-to-1, it's infinity to 1. There's infinitely many points that map to that one point in the w plane. So if you want to invert this map, you have to make a choice of one of these values. The principal logarithm chooses the one that's in this strip here. But you could just as well write down a logarithm that went to this point here. What would that be? Log, let's call it log Sharon of w.
Can you just spell my name right?
Oh, that's right. It's like Sharon Joy. Is it with a G?
No, just Sharon, but with an I.
We should add a G.
No, my mom thought about putting an apostrophe, but I'm glad she didn't.
It is special. It is special. But log Sharon would just be the ordinary log plus 2 pi I. Because it's just shifted up. Okay. So that's one thing, right? You can think about restricting the domain to make the exponential a one-to-one function onto the complex plane, right? But people with more of an imagination say no, don't do that. Instead, leave the domain alone it's an exponential. The domain ought to be the whole complex plane, right? So instead, I'm going to do some funny business over here. I'm going to invent some new space over here such that it becomes one-to-one. And so that's the idea of the Riemann surface, is basically to take these different arrows and kind of separate them. And so you instead of having one copy of the complex plane over here, you have kind of like an infinity of them, and they're connected together. The picture here is something like a spiral staircase, like a spiral ramp. And on each sort of little bit of the spiral, you map the complex plane onto, and then the next branch of the log goes to the sort of the next part of the spiral, and on up it goes. So you're thinking about gluing together, in some sense, like this to the next piece. And anyway, so in your next course in complex variables, you should actually look at that more deeply. I'm going to stop talking about it here for now, because we have other things to do today. So I hope I have confused you sufficiently much about branch cuts. We'll move on now. We do eventually need some of these ideas to do certain integrals. And I do want you to think more about the idea of a local inverse. I think that's an important part of math. And this is not just a complex analysis thing, right? The problem of finding a local inverse is a problem for all parts of math. Well, parts I'm familiar with. Again, the branch cut is, it's just, we have a function which is multiply valued, right? So the branch cut essentially just amounts to choosing one of those values, so that, once you make that choice, then you can look at the inverse. But that multiple value came from some subset of the domain, so the selection of a branch cut goes hand in hand with the restriction of the domain. So that part of the domain picks out, maps to that value. All right. But you can read what Gamelin wrote about the creation of the Riemann surface for the square root function. That's more complicated because it kind of like the Riemann surface for the exponential function is easier because it just keeps going. It never really gets back where it went again. It just kind of keeps going up. But the Riemann surface for something in the square root involves this, like, it loops back on itself. For me, it's harder to visualize anyway. But all right. So sine, cosine, cosh, sinh. How are these defined in the complex domain? All right. Any ideas? Oh, I hid my phone in my pocket. I'll do that sometimes. Phew, half hour left, good. All right. I think these are actually much easier topics. To me, the idea, this whole discussion about branch cut and everything, to me it's very complicated for you guys because you haven't thought a lot about local inverses, I don't think. This, on the other hand, is a little bit simpler. So here's the starting point. If we have e to the I theta, right? That's cosine theta plus I sine theta, right? And if you think about this, e to the minus I theta is equal to cosine theta minus I sine theta by even oddness of sine and cosine, right? So if you take these identities, right, and you add and subtract them, what does it give you? The double angle formula is, well, eventually, yeah. But first we get this, right? So you can find a formula for cosine and sine in terms of imaginary exponentials. And if you're very foolish, you try to teach this to Calc 1 students. I do. I think it actually should be taught in high school, honestly. We've known since the middle of the 19th century that complex numbers are rigorous and worthwhile and simplify computations. Why aren't we teaching them as soon as we can? Why are we making things more complicated than they need to be? We should listen to Gauss. He told us in 1830, get over it. Start using them. It's high time we did. But we would have to have high schools populated by teachers who understood complex numbers. And therein lies the problem. So, at least in America. I don't think it's a question of pay. I think it's a question of desire by society. I mean, I think you could pay 30 Indian high school teachers on the wages of one American. I'm just guessing. Maybe India's a bad choice. Pick your favorite third world country,
Zimbabwe.
There you go. Oh, wait a minute. India's not third world. I'm going to have to take this video down. Oh, my goodness. I'm in so much trouble. Anyway. Can you? No, do not. Okay, so these are formulas. But here, I'm just assuming theta is real for the moment. Okay? But these motivate our definition. We just say, okay, so whatever cosine and sine should be in the complex, we should just replace theta with z and expect that that's a good definition. It turns out that there's a justification for that later as we study more, okay? But so in some sense, these definitions I'm about to write are transitional. I mean, they're temporary, but in another sense, they're always good. But I mean, you can debate whether or not these are the right definitions or not, right? But they're nevertheless, these are equivalent to whatever definitions you might come up with. So there you go. So here's our definition. The complex sine, or complex cosine, cosine of z is equal to 1/2 e to the iz plus e to the minus iz. And the sine of z is equal to 1/2i e to the iz minus e to the minus iz. So there you go. There's your definitions for complex sine and complex cosine. Now, something else we should talk about is, in the real case, what do we have? E to the x, right, is equal to what? It's equal to cosh x plus sinh x. Why is that? Well, let me be less jumpy here. E to the x is 1/2 e to the x plus e to the minus x plus 1/2 e to the x plus, minus e to the minus x, right? This identity simply expresses the fact that the exponential, which has a domain which is symmetric about 0, can be expressed as a sum of an even and an odd function. Okay, so if I'm going to define cosh and sinh for students, I'll introduce it this way. I'll say, cosh, it's just the even part of the exponential. And sinh, that's just the odd part of the exponential. If you haven't seen these, you have seen these before. I mean, if you haven't seen these before, I need to find out who you had calculus with and go harangue them. But just to remind you, cosh is basically like goal, and sinh is basically like a cubic. Okay, so I mean, not quite, but that's essentially there's your review of what cosh and sinh look like in the real domain, right? Key points here: cosh is never 0. The smallest it can be is 1. Sinh can only be 0 one place. Sinh of 0 is 0, and that's the only place sinh is 0. Sinh is 0. For a real variable, though. I'm talking about real variables right now, right? So care to guess what the definition of complex hyperbolic sine and complex hyperbolic cosine are? Cosh of z is equal to what?
1/2 e to the I theta.
Oh, no. You had me at 1/2. 1/2 was good. The e was good.
And e, yeah. I was going to say you got it.
There's definitely a z involved. I want formulas in terms of z.
IZ.
No i's. Just z, yes. So basically just take the x and replace it with z. Just like I took theta and replaced it. If theta was a real variable over here, I replaced it with z. Same thing here. So there you go. That's the hyperbolic sine and the hyperbolic cosine as defined in the complex domain. So there's your definitions. Now, of course, you can also define hyperbolic tangent and tangent in terms of the quotients of sine and cosine or sinh and cosh, usual way. But in the remaining time today, I want to see what identities we can derive for these and what we can say carefully about these functions, right? I always ask questions about these on tests. These are important examples. You want to understand them backwards and forwards and upside down. All right, so they're pretty easy to work with too. So first of all, how are they related? Cosh of z is what in terms of cosine? Or perhaps the other way around. I mean, this is what? Cosine of what? Yep. See, because if you take iz and you put it in the place of z here, you get I squared z, which is minus z, and you get minus I squared z, which is z. So e to the z plus e to the minus z, but they're in opposite order. How about the sinh in terms of sine?
It's also sine of iz times I.
So iz. Now let's not try to do it all in our head. Let's do sine of iz. Let's work it out here. Sine of iz is 1 over 2i, right? E to the I iz minus e to the minus I iz, right? Okay, so what's that? That's 1 over 2i. E to the minus z minus e to the z. But you see what that is? That's I over 2 e to the z minus e to the minus z, which is actually I times what? That's I times the sinh of z. So if I want to say sinh of z is equal to sine of iz, I got to put the I on the other side, right? So it's actually minus I. It's probably worth me writing down while we're at it. Just go ahead and write down the opposites. So of course the words. So cosine of iz is cosh z. That's fine. All right. And then sine of iz is actually equal to I sinh of z. You might also want to be able to write it in terms of cosine of z in terms of sinh and cosh of iz, right? I'll leave those to you guys. Okay, so that's the relation between those. Now, can you express? My goodness, what's wrong with me today? Goodness gracious. Now, cosine and sine, the complex cosine and sine, they do come with some new wrinkles. Some of the things that are true about them are the same as were before, but other things are really, really new and different. Let's work it out in terms of the real components. Let's actually study cosine for a second here. I'm gonna give you a spoiler alert here. Cosine of z is not bounded. That's what we're about to show. So I've got cosine of z is cosine of x plus iy, right? So I'll just keep with the definition here for a second. That's going to be what? 1/2 e to the x, e to the iy, plus e to the x, e to the minus, oh, goodness gracious. All right. So 1/2 e to the x plus iy plus e to the minus x minus iy. So of course, you can rewrite that. 1/2 e to the x, e to the iy, right? Plus e to the minus x, e to the minus iy. Okay, so this isn't the greatest formula to understand its modulus, but we can see some things from this. Just look at it. You can tell some things, right? As x goes to infinity, we have the modulus of, well, we have what? e to the x goes to infinity, right? And that it stands to reason then that cosine blows up as you let x get really large, right? And conversely, as x goes to minus infinity, that makes e to the minus x blow up, right? So either coming or going, cosine gets huge. However, I don't know, this to me is not, I mean, you can think about it in these terms, right? But I have a hard time seeing anything terribly convincing this way. There's a better way to look at this. So here's, I'll show you. So we have cosine of z is cosine of x plus iy. The adding angles formulas are also true for complex sine and cosine. You can prove that. I can prove the adding angles formula for cosine by direct algebra on the definition, okay? I can expand out what does it mean cosine of z plus w. That will give me like exponentials of z plus w, and then through the laws of exponents I can derive the laws of addition for cosine and sine. Those are good like test questions or homework questions. I forget if I made them either. I don't know, I haven't written your test yet, so. But anyway, so cosine of x, cosine of iy, right, what is it? Cosine of a plus b is cosine a, cosine b, minus sine a, sine b. This is an identity which is in fact true still in the complex domain. Right? But this is a little bit nicer. We're getting towards a real formula for it. Let's see here. So what's cosine of iy though? It's cosh of y, right? And how about sine of iy? Sine of iy is what is it, Malia? Oh, z equals to y. So it's just a special case. I mean, z is a complex variable. Certainly iy is an example of that. I mean, y equals to z is a special case, but a case nonetheless. So minus I sine x sin. Now, I can't, reversing that logic is more dangerous, of course. I mean, these were not derivations, these were definitions. See, I went from theta to z. Once you accept this as a definition, then this is immediately just a consequence of the definition taking z equal to theta. But okay, now that I have this, cosine, cosh, sine, sinh, these are all real functions of real variables x and y. So you can calculate the modulus of the cosine from this expression, right? What is it? Modulus of cosine z. See, because when I say a complex quantity is not bounded, what am I talking about? I'm talking about its modulus, right? Because complex numbers are not ordered. If I ask you which is larger, 1 or I, you should go, I don't know. You told me the complex numbers can't be ordered. Well, don't just tell me what I told you, but they both have the same modulus, though, right? So 1 and I both have modulus 1. So we can order the complex numbers in a sense, but it's not strictly speaking, Anyway, so if you look at circles with respect to the origin, it's you can see which one is closer and further away from the origin. So they are ordered in that sense. But anyway, so modulus of cosine is what? It's cosine squared x cosh squared y plus sine squared x sinh squared y. Because that's the x squared plus the y squared, the real squared plus imaginary squared. And of course I should have modulus squared. I write that. And clearly that's not bounded, right? Because cosh and sinh get arbitrarily large as y goes to infinity. So, and there's some similar discussion to be had for sine z, right? You can also show sine z is a sum of cosines and coshes and sinh squared, and it's also not bounded. And I think that I'm depriving you of some more clean formula right now. See if I can find it. No, that's what I have in the notes. Oh, yeah, I think I can get rid of the. I claim here that I can get rid of some of it. There's a way to simplify this using. Let's see here. I can boil it down to cosine squared plus sinh squared. Cosine squared of x plus sinh squared of y. Let's see here. How would you do that? I mean, there's various ways to attack this. I'm gonna pick on this piece right here. Sine squared I can rewrite as 1 minus cosine squared x, right? And so what's this going to be equal to in view of that? It's cosine squared x, parentheses, cos squared y, what? Minus sinh squared y. Aha! What? Then plus what? Plus sine squared x, right? But this guy, if you know anything about hyperbolics, you know is 1. So this is the hyperbolic Pythagorean identity, if you like. That's 1, and so we just get cosine squared x. Excuse me. I did something wrong. Oh, this isn't sine squared x. This is what? Yeah, this is sinh squared y, right? Yeah, you're like, hey, it works out to 1. No. That would be very disturbing, too, if the modulus of complex cosine was always 1. That would be very strange. So cosine squared x, sinh squared. It's like, wow, this is a new profound relation. I mean, wow, what can I do with this? No, in fact, that simplifies to this. And there's a similar simplified formula for sine in the notes, okay? But, of course, sinh blows up, right? I mean, cosine of x is bounded between plus or minus 1, but sinh goes to infinity as y goes to infinity, or to minus infinity, that's squared. All right, so so here's some claims for you. You know, cosine of z plus w is cosine z cosine w minus sine z sine w. And also the sine of z plus w is equal to sine z cosine w plus sine w cosine z. And there are similar identities. For cos and sinh. All right. What is the well, here's something that's surprising, right? So we just got done telling you cosine's not bounded, sine is not bounded. But here's something interesting. Cosine squared z plus sine squared z is equal to 1. But to me, that's kind of surprising. I just got done telling you this is unbounded. Well, cosine of z is unbounded. By the way, if cosine of z is unbounded, cosine squared of z is also unbounded. This guy's unbounded. This guy's unbounded. And yet, these things still conspire together to always give you this constant 1. That's kind of surprising to me. How would you prove that cosine squared plus sine squared is 1? It's probably useful for us to do that. So I'm hoping you're starting to see some things as we go on in here. One is that sometimes you can make arguments at the level of complex variables, right? As we related Cauchy and Sinch, we didn't need to get into x plus iy. Nothing to do with it, right? On the flip side, to understand the modulus of cosine z, I really had no choice except to get into the real and the imaginary parts, right? That I had to do that in order to see what's going on here. So, I would say descending to this level of notation is a last resort. If we can make an argument at the level of complex notation, it's usually better and easier. But it's not always possible. So here, cosine squared z is 1/2 e to the iz plus e to the minus iz, quantity squared. So you FOIL that out, what do you got? You got 1/4 e to the 2iz plus 2 plus e to the minus 2iz. I'm using the laws of exponents that we have supported in previous lectures, although I haven't proved in their entirety. You can prove those laws of exponents by relying on the usual laws of exponents and the adding angles formulas for sine and cosine. So you FOIL that out, and that gives you, there's a minus 1/4, right? So when you think about squaring, you add the exponents, right? So the cross terms have e to the iz and e to the minus iz, but that gives you e to the 0, which is our old friend number 1, right? If I was at another school, I would say you guys are all looking out for number 1, right? But here we try not to do that. But for the purpose of this proof, we're looking out for number 1. So your cosine squared z plus sine squared z then is equal to what? As you can see, these cancel, because there's a minus out here. But then I get 2, I get a half, minus a half. In other words, un. And there you have it. Both of those things are diverging in some sense as you go to various parts in the complex plane, but they're kind of balancing each other out somehow. That's what's happening, because the modulus of their sum is always 1. Anyway, if you want, I loaned to Lorenzo your copy of Churchill. She has it. I have several more copies in my office if you want. In Churchill, there's like a whole section that's just on, well, kind of like my notes. There's a section just on sine and cosh, sinh and cosh and quotient. I mean, there's tons of identities that are known for these in standard homework problems. I've assigned you some subset of those, but it's the more you know is the more powerful you are. Anyway, I hope that's enough for you to get started on all this. Anyway, I'll collect your homework Wednesday. Thanks, guys. Oh, I have somehow forgotten to define z to the c, which is what? E to the c log z. So that's what you need for the last problem. That's the set of, that's the complex power function. So I guess I need to talk about that at the start of next class, since I have somehow forgotten today. Curses. Anyway, the homework is still due Wednesday. The answer is in the problem. You can figure it out. It's not that bad. Don't mean to give you false hope there. You can cut it off. Yeah.
Should Wonder Woman hit the record button again? To stop it?
Yes. Yes, Wonder Woman should hit the record